This is ECE 341, Part 1, Lecture 11. Last time we were introducing a variety of models for discrete random variables, these families of random variables. We looked at models such as Bernoulli random variables, um, we had binomial, we had geometric, we had Pascal, we had Poisson. Today we're going to continue looking at discrete random variables. We'll begin though by taking a look at the idea of summations. In working with discrete random variables, we oftentimes need to evaluate sums. That's how we get probability totals. We sum up things like the probability mass function over the values that are of interest. And sometimes those sums can get large, and we need to have a few tools available to us so that we can carry out those sums in an efficient way. So we'll go ahead and take a look at some common sums. These also appear in Appendix B of the book, so you might take a look there. The first and probably one of the most important is the geometric sum. The geometric sum takes the form of having some number, let's call it w, raised to some power k, and we're going to sum over k going from some lower limit a to an upper limit b. The geometric sum formula says that that entire sum, regardless of what are a and b, can be evaluated with the simplified formula of w to the a minus w to the b plus 1 over 1 minus w. So for example, I might look at something along the lines of, I would like to sum up 1/2, right, to the k for k going 3 to 10. If I was going to evaluate that by the straight sum, I'd have to take k equaling 3, then k equaling 4 and 5 and 6 and 7 and 8 and 9 and 10, and put all those terms in there. I would like to avoid a lot of that work, and the sum formula says that this would just be equal to 1/2 to the third minus 1/2 to the 11th over 1 minus a half. And that has a fixed computational load. You'd probably still want to use a calculator to do that final calculation, but much better than having to carry out all those sum terms. Think about the difference this would make if you had a sum going from 0 to a million. If you evaluated that sum explicitly, you'd have 1,000,001 terms that you'd have to sum up. In this alternate form or this closed form solution to that sum, you only have a fixed number of calculations and they can be done pretty quickly. If we want to get an idea of why this sum formula works or why it is the way it is, let's go ahead and do a very quick proof on this. I'm going to call S the sum that we're looking for. That's that sum k going from a to b of w to the k. If I break that out term by term, when I put k equaling a, the first term is w to the a. The next one, we increase the variable of summation by 1. That's going to be w to the a plus 1. And we're going to keep adding them up until we hit the upper sum limit, right? And that is b. So we're going to get up to wb. I'm going to now employ a mathematical technique. I'm going to multiply that sum of interest s by the number that's being raised to all these values, right? So w. So I'm going to look at ws. If I do that, that's just going to be w times the line I have above. So w to the a, that's this guy, right? Multiplied by w just gives me w to the a plus 1. And we keep doing that all the way across, and we end up getting to a wb, and then finally a wb plus 1. So every term in the upper line, right, is just increased in its exponent by 1. Now, if I subtract these two sides, if I take this first piece s and I subtract off ws, what do I get? I get s minus ws. So I'm going to work with that and see what happens. What's nice about this subtraction is if you look at the upper line, that upper line has a lot of shared terms. There's a wa plus 1 on the top and minus a wa plus 1 on the bottom. And they're going to keep going across on all those diagonal terms, and all of those guys are going to cancel. So we're going to get a lot of cancellations going on in there. And really the only terms that are left are this w to the a and w to the b plus 1, regardless of what is a and b. I do think that it's pretty obvious that the assumption here is that b is going to be greater than or equal to a. So we aren't looking at the case of b being less than a. That just wouldn't be too terribly useful. So if I go ahead and then carry out the right-hand side with all those term cancellations, I'm left with just w to the a, right? And I'm going to have a minus w to the b plus 1. If I go ahead then and factor out the s on the left-hand side, right, I'm going to get s times 1 minus w. That's equal to the right-hand side, wa minus wb plus 1. And if I solve for the s by dividing both sides by 1 minus w, I end up getting that geometric sum formula that we had seen earlier. That's this guy right here. So pretty easy to derive this guy. Definitely a better form than doing explicitly all terms in that sum. Much easier, much better to use this closed form fixed computational load version of that sum. There's quite a few other useful sums. We're going to just pick a few that are probably most useful to this class. The first one I'd like to look at, in addition to the geometric sum, is this idea of just summing up a constant. I'm going to go ahead and sum a constant 1. If you had a different constant, you would just scale this whole sum by that different constant. You could pull it outside of the summation and just multiply this result. So here we're going to sum up 1 going from 0 to n. If you just do that explicitly, the k equaling 0 term is this first one, k equaling 1 is the next one, and we keep adding them up until I get the k equaling n term over there at the end. There's a total of n plus 1 terms because 0 is a term, and that term matters. So I have a total of n plus 1 values, and they're all equal to 1. So what happens when you take 1 plus 1 plus 1, n plus 1 times? You just get n plus 1. So that one's a pretty straightforward one. If we add up a constant, right, however many terms there are of that constant, you're going to just take that number of terms times whatever the constant is. And in this particular case, I left that constant as 1. The next one we'll look at is a sum from k equaling 0 to n. But now we're going to sum up that sum variable k, right? And this particular sum ends up evaluating to n times n plus 1 over 2. This one also is something that we can at least get a picture or visualize really pretty easily. So if I take the k equaling 0 term, that's not going to contribute at all, right? K equaling 0, if we're summing up whatever is k is equal to 0, that doesn't add anything. So actually this whole thing is going to be, whoops, let's go ahead and make this into a pen that can be useful. This is also equal to a sum k equaling 1 to n of k, just because the k equaling 0 doesn't matter. So k equaling 1 then, what are we going to add? We're going to add 1. I'm going to let that be this little dot down here. There's 1 value. When k becomes 2, I'm going to be adding 2 things. So I'm going to make 2 little dots. When we get k equaling 3, that's going to be 3 of those guys. So I'm going to put 3 dots. And we can keep going on until we hit n, in which case we are going to have a total of n dots. I'd like to count up all those dots, and I'm going to do it in sort of a clever way. I'm going to go ahead and extend those dots in an equal area kind of way. That's that red stuff. So I've shown a little red triangular looking piece there, so it would have a bunch of dots in there as well. So there'd be n on the bottom going all the way until we just had a single one on top. And that's going to go out to an index value of n plus 1. What that makes is a rectangle, right? And we know a rectangle has the total number of dots. If we have a dot for each integer on the rectangle side, one side is n in number, and the other side is n plus 1 in number. The total number of dots for that rectangle is n times n plus 1. And because we were looking for half, the ones that aren't in the red, right, we just divide that by 2, which is how we, again, get this overall response or this overall formula here of n times n plus 1 over 2. Nice graphical depiction of that. The last one I'm going to give is not going to be shown with a proof. The proof is just a little bit inconvenient, and this one doesn't show up terribly often, but let's go ahead and do it anyway. This is the sum of k equaling 0 to n, and instead of doing k, we're going to do k squared. Turns out this guy is an n times n plus 1 times 2n plus 1 divided by 6. So certainly this would be a lot easier if you had to go k going from 0 to 1,000, right? You would definitely want to use this closed form version instead of doing that individually term by term by term. So equipped with these tools of sums, all these different sum forms that we have, it just assists us when we are working with these probability mass functions and trying to compute probabilities. We have some numbers that we have to end up summing up. They oftentimes fall in a form that is consistent with one of these standard forms or some version of them. And it just gives us tools in order to evaluate them conveniently and efficiently. Let's go ahead and get back to the discrete random variables that we were studying beginning with chapter 3. We had already introduced the idea of a probability mass function, which we call px of x, and that's one common way to understand a discrete random variable. If you recall, that probability mass function, px of little x, right, just tells us what is the occurrence probability for the random variable x taking on a particular value, little x. So it's just the probability, right, that x equals little x. It gives us an idea of how probability is distributed across the different values of x. There are other ways that we can use to describe a discrete random variable, and another common one is something called the cumulative density or cumulative distribution function, the CDF. And so let's go ahead and take a look at the CDF. The CDF, by notation that we're going to follow in the book here, is going to be notated by a cap f of cap x, and then you have, as a function of this guy, little x, the observation. So this is the CDF of random variable x, right, as a function of the different observations, little x. What is the cumulative distribution function? That cumulative word out front just means an accumulation of probability. So instead of being like the PMF, which is the probability that X is a particular value, right? The CDF is the probability that X is less than or equal to that value, the accumulation of probability up to that particular point, little x. So if you think a little bit about this, you'll recognize that both the probability mass function and the CDF have equivalent information. They're just presented a different way. So that is shown up here in the note. It says if you have a probability mass function, you can obtain the corresponding CDF and vice versa. They have equivalent information. They're just two sides of the same coin. They have the same basic information in it. I will say that sometimes, right, sometimes a probability mass function is more convenient to use for some kinds of calculations, and sometimes a CDF is more convenient to use for certain calculations. And so really these are just two different tools that we can use based on what kind of application we're working on and which is more convenient. I will say that primarily for many people, they probably prefer working with the probability mass function rather than the CDF. But the CDF, like I said, has equivalent information, and so you could get by totally with the CDF. Let's take a look at some of the properties of a CDF. One of the things that we can think about on the CDF, we're going to go ahead and do this for a discrete random variable, and it's going to have some range space. Let's just have it have a bunch of values, x1, x2, going on to whatever, and let's let those be in a sorted order. x1 is less than or equal to x2 is less than, and so forth. So, for example, you could have a discrete random variable x that was the outcomes from rolling a six-sided die. The range space there would be x1 is being 1, x2 being 2, all the way up to x6 being 6, something along those lines. Because the CDF is an accumulation of probability, if I look at that accumulation of probability starting way over on the left-hand side, there's nothing to the left of minus infinity. So no probability has had a chance to accumulate. The accumulation, right, that CDF should start out at a value of 0. There's no way we can have accumulated any probability if we haven't started moving forward from the leftmost side on that set of real numbers for which x is defined. On the other side of it, if we go fx out to infinity, think about what that means. That's the probability that x is less than infinity. X is always a real number. What's the chance that it's less than infinity? Well, there's nothing greater than infinity, so that's going to be an accumulation of all the probability, and we already know what that is as well. That should be 1. So the CDF starts at a value 0, and it continues on until it hits a value 1. We can come up with a second property here, so I labeled this one B, and I'm just going to say for a value x prime, which is to the right of, so in other words, it's greater than or equal to x, we can say that the CDF of that value x prime, when it's compared to the CDF of x, what kind of relationship would they have? Well, it would have to be greater than or equal to, right? Because x is to the right, that just means we're accumulating more stuff, right? Now, it might be that there's no probability to accumulate, in which case it's going to hold flat. But if I hit some other value that was possible, we would accumulate whatever probability was associated with that value, and that would make the overall probability total go up. So this is something that tells us that a CDF function f of x is what is going to be called monotonically non-decreasing function, non-decreasing. So if you look at a CDF, right, when we go off to the left, it starts at 0. When we go to the right, it ends at 1. It is always getting no smaller than the previous value. That means it's always cruising along, and it's just going to keep stepping up, stepping up, stepping up, stepping up. It never goes back down. Okay, so if you ever saw a CDF function, or we're trying to evaluate a candidate CDF function, if it all of a sudden went from one point moving left to right, if the CDF values went down, right, we know we'd be in trouble. And in fact, that would correspond to having negative probability, which we know from the axioms of probability can't hold. Another property that we can see of these CDFs, in fact, a lot of these properties are deriving exactly from the axioms. You can leave that as an exercise to see which axioms exactly lead to which properties. But let's look at this third one, C, as I've listed it here. If I have some observations xi that are part of our range space, so these are values that can occur, right? And I also look at some positive and a small positive number epsilon. I can say the following, that the CDF of xi minus the CDF of xi minus that epsilon, what does that mean? I'm going to look at the accumulation of probability up to that value xi, and then I'm going to subtract from that the accumulation of probability up to just before xi. What should that give us? Well, that should give us the probability that x equals xi, right? We had the accumulation up to and including xi, and then we got rid of everything that was accumulated up to but not including xi, and that should just give us the overall probability that x equals xi, right? So this tells us that fx has a jump discontinuity at values in the range space xi with height equal to what? That is that px equaling xi. And if you remember, px equaling xi is really the values that we just get from our probability mass function. So that tells us these probability mass functions, right, can be used to try to help us figure out how probability accumulates. There's no surprise there. We can get the probability mass function values, right, by taking a look at all these steps that occur in our CDF. And we get step occurrences because it's a discrete random variable. Later, when we get to continuous random variables, we're going to see the behavior slightly different. Another one that we can get in here is this idea that fx of x is equal to fx of xi. Now, what's the difference here? Xi is a value that could occur like a six-sided die. That would be 1, 2, 3, 4, 5, 6. Here, an x could be any value on the real number line. So fx of x is equal to fx of xi as long as x is between xi and just before the next value that could occur, xi plus 1. So what does this tell us? It tells us that the CDF is flat. Whoops, let's put this into a highlighter mode. So we know that the CDF is flat between values that are part of our range space. We can also build out of this, and this has to do with these inequalities, whether it's less than or equal to or less than. We can also build out of this that the CDF is a right continuous function. This D, this fourth property that I've shown, the fact that the CDF is flat between observable values of our random variable, might be a little bit hard to see. So I think a concrete example can help us out with this. Suppose that I flip a fair coin. So what does a fair coin do? It has two possibilities, tails or heads. I would like to make this into a random variable, so I'm going to go ahead and assign tails to a value x equaling 0 and heads equal to a value equaling x equaling 1. We can build from that, and we've done this before. This is basically a Bernoulli trial, right? And so we know the probability mass function for a Bernoulli random variable, px of x, is going to be a half for those two observed values, 0 and 1, right? And it's 0 otherwise. So that's one way of fully describing this random variable through the probability mass function. What's the range space on this guy? What are the values x can take? Well, x can take a value of 0 and it can take a value 1. And so we're going to call those two values x1 and x2, something along those lines. That would be consistent with what these xi's were previously when we were looking at some of these properties of the CDF. What does the CDF look like? A CDF is an accumulation of probability up to and including a particular point. So if you take a look at this particular guy, right, if I take a look at this overall probability mass function, what is the first value that can happen? Well, the first value that can happen is 0, right, which corresponds to a tail on that coin. So from minus infinity less than x less than 0, right, there is nothing to accumulate probability on because none of those values happen under this experiment, under this random variable. These are not parts of our range space. No probability can accumulate, and that means my CDF is going to be 0. That's shown down here. I've got my CDF being 0 for any value less than 0 because I haven't hit anything in that range space in that S of x, okay? When I hit x equaling 1, now what do? The second I hit 0, what is the CDF? The CDF says the probability that x is less than or equal to that particular value, in this case, x1 equaling 0. So what's the probability that x is less than or equal to 0? Well, 0 is the only one that can happen in there, and I know it has half probability. So all of a sudden, that CDF jumps up to a value of, well, a half. And so we see that sitting there right there. At 0, we get that jump discontinuity. And the fact that I get a jump discontinuity at that point is my indicator that I've just hit a value that has some possible probability. It has some non-zero probability. That jump is an indicator that that value is part of our range space. So when it comes to discrete random variables and you start looking at the CDFs, anytime you see a jump in that CDF, right, we know that those are values that can occur with non-zero probability. Well, all the values between 0 and 1, as I continue with my CDF, that CDF going at something like, say, 0.5 or 0.75, 0.5 and 0.75, we'd be saying, what's the probability, the accumulated probability that x is less than or equal to a half or less than or equal to 0.75? Well, there's only one value, right, that's less than 0.75 or zero point 0.5. That's x1 equaling 0, and that has probability of half. So that guy stays flat, right? It stays flat until the next value that is a part of this range space Sx. That occurs at x equaling 1, which we called x2. At that point, we get the other half of the probability, so we get that jump again, and it stays that way for forever because we've now accumulated all the probability. We've got 100% of it. So what did we get? We got something over here that at f of minus infinity, fx of minus infinity, that started at 0, fx at infinity, it hangs out at 1. This thing never goes down, right? It never decreases. It only can stay flat or get bigger. So that's that monotonically non-decreasing part of this guy. And we see jump discontinuities that are corresponding to the probability of particular points, things that are in our range space. These CDFs will look like a staircase leading off to the right, always going up, and they plateau out at a value of 1, something along those lines. Okay, so using the CDFs, it's really easy to compute probabilities of being in some interval. This is another theorem in the book, so you can call it a theorem or you can just call it a useful fact. If I have some value b greater than or equal to a, if I take the accumulated probability up to b and I subtract off the accumulated probability up to a, then that's going to give me the probability that x is between b inclusive and a not inclusive. Okay. I will make this little kind of caution out here. It does matter whether you use less than or equals. These are discrete random variables, and these inequalities, whether they're a strict inequality or not, do matter. So you do have to pay attention to this. The f of x is inclusive up to a point, and so if I subtract off, in this case, we subtracted off all the accumulated probability up to and including a, what was left over had to be anything past A, right? And so we would get something along those lines. So let's go ahead and note then from this that you can get back to the probability mass function. So if you wanted just the probability of a particular point, px equaling A, you could take that's just our probability mass function pxa, right? You could take the CDF of our random variable at A, and then we could subtract off just a smidgen to the left of A, the CDF. So go back over here to this other one where we were talking about a coin toss, right? If I wanted to know something like what? If I wanted to know the probability that x equals 1, how could I do that with a CDF? I could do that as fx of 1, and I could subtract from that fx of just a smidgen to the left of 1. What is fx of 1 equal to? Well, I can go back in there and I can take a look at that. Fx at 1, we can see that that's that closed dot. That means it's included in there. That guy is equal to 1, right? And if I look just a little to the left of 1, that's somewhere over here, we can see that just going a little to the left of 1, we drop down. That's that jump discontinuity. That's going to be a half, so I'm going to get 1 minus a half equals a half. That's the probability that x equals 1, and that certainly matches what we saw in our probability mass function. So again, you can go from a probability mass function to a CDF, or you can go from a CDF back to the probability mass function. And it has to do with the size of the jump discontinuities in that CDF, something along those lines. Let's do another example, one that's a little bigger, and it's a little bit different. I don't know that this is necessarily going to be the smartest assignment of a random variable, but sometimes a little bit of abstractness in an example does demonstrate some utility in how we set these things up. Okay, so let's go ahead and take a look at a case where we have some large box. So that large box really means that as I pull stuff out, we aren't going to substantially, or we will assume we won't change at all the probabilities of the components that we're pulling out of there. So this is a big mixed up box. We could go around the double E department and go to all the labs, and we could pick up all the components off the floor and laying around on the tables and everything like that. And we could do that over 100 years, and we'd end up with this big box. And that box we're going to assume has a bunch of resistors in it, capacitors, some inductors, and some transistors, something like that. Now you could draw, you could just stick your hand in there and you could pull a component out at random. And we're going to assume for this particular example that if you took that big box and you just swung your hand around in there and you pulled a component out, that 10% of the time you're going to get a resistor, and that 30% of the time you're going to get a capacitor, and 20% of the time you're going to get an inductor, and 40% of the time you're going to get a transistor. Okay, so if I sum all of those guys up, right, if I sum all those probabilities up, summing all of those probabilities up goes to 1, and none of them are negative. So it's looking like a pretty good model for this particular experiment. I've got 4 different types of components around a big box, and they each have a particular likelihood, and all of those likelihoods sum up to 1. Okay, I'm going to call in this particular case the resistors an R, the capacitors a C, the inductors an L, and the transistors a T. That will just simplify part of the labeling that I'm going to do later. We can start thinking about doing things like PMFs and PDFs or PMFs and CDFs right now. But I think at this point we would not be successful in doing something like a PMF or a CDF. Why not? Well, because right now, the way I have the experiment laid out, I have things like an outcome of an R, a C, an L, or a T. And I know they're probabilities, but R, L, C, and T, right, are not numbers. And a random variable must be a number. So we need to have something that maps these outcomes, a resistor, a capacitor, an inductor, or a transistor. We need to map these guys to numbers so that we can make this a random variable. Once we have that random variable, then we can look at that mapping of a probability mass function, or we can look at that mapping of a cumulative distribution function, something along those lines. So each of those observations, I'm going to call them C, okay? So each of those observations, R, C, L, and T, right, are not random variables because they are not real numbers. We can make them into, or we can map them into a random variable, and I'm going to go ahead and call that random variable X. We can do that according to some mapping rule, that random variable. This is how we first introduced that. And so I'm going to just say random variable X based on those observations C, right, are going to be the values of 5, 0, minus 1.5, and 2, depending on whether we observed a resistor, an inductor, a capacitor, or a transistor. So this is where this is a little bit abstract, why we would want to assign resistors to 5 and capacitors to minus 1.5. I haven't given any justification for that. We're just showing an example of where we do that. So we now have a random variable X, and different numeric values of that X correspond to these different components, resistors, inductors, capacitors, or transistors. So let's go ahead and use all of this information and see if we can determine and sketch the CDF function fx of x, something along those lines. So let's go back to what we had before initially. We saw that there were resistors, capacitors, inductors, and transistors, and they had particular probabilities, right? We know that a CDF is an accumulation of probability. So if I'm going to be thinking about accumulations of probability, I'm not going to accumulate anything until I hit the first value x that is possible. As I scroll through that list of values for the random variable, 5, 0, minus 1.5, and 2, what I notice in this particular case, right, is that minus 1.5 is the first thing that can happen. So as far as this mapping for this random variable, capacitors would be indicative of the first number that we would see, a minus 1.5. That means you got a capacitor, something along those lines. Anything before that, any x value before that, would have a CDF equaling to 0 because there's no probability to accumulate. Nothing has happened for values x less than 1.5, minus 1.5, right? You look through this list, there is no value less than minus 1.5, so there could be no probability associated with that. So how could I do that? I could come down here onto my graph here, and let's go ahead and just do this into red, okay? Anything before 1.5, right? There's been nothing to accumulate, and so I know I'm going to get a value of 0, something along those lines. So I can also translate this into a mathematical statement. So I started with part of the sketch, but I can also translate this into my expression for fx of x, my CDF. And so I'm going to say that the CDF is equal to 0, right, for x less than minus 1.5. So we have no accumulated probability until I hit 1.5. Once I hit 1.5, well, then I'm going to accumulate all the probability, right? I'm going to accumulate all the probability associated with capacitors. And what were the probabilities associated with capacitors? It's 30%. So we're going to get a jump, right? We're going to get a jump of 30% when I hit that minus 3.5. Minus 3.5 corresponds to a capacitor, so I'm just going to throw that down there to remind us of that. And then we're going to come up 30%, right? So if I do that here, I'm going to go ahead and put in that value, right, at 30%. So this is 0.3, something along those lines. And I accumulated that probability because minus 1.5 of my random variable, which means a capacitor, does have a non-zero value of probability. So we will get an accumulation. We're going to get a jump in this CDF. Okay. How long does it stay at that 0.3? Well, the next value that we would see in this particular case is what? It's 0. So that would be indicative of an inductor, right? So no more probability will accumulate until I hit a value of 0. So let's go ahead and draw that out. Until I hit a value of 0, right, I am going to just stay with that accumulated probability that I had from being a capacitor. Once I hit 0, we knew that that was an inductor, something along those lines, and we'll get the inductor probability here in a minute. So this helps me fill out the next part in my CDF description. I know it's going to be equal to 0.3. That's a step up, right? This is that monotonically non-decreasing nature of this guy, and it's going to get a jump discontinuity. That jump discontinuity comes at minus 1.5 less than or equal to x less than 0. And it needs to be less than 0, because if I included 0, I'd need to include the probability of 0. And because 0 is a thing that happens, it has non-zero probability, it would no longer just be 0.3. Okay, so we're going to continue with this. I think we get the basic pattern here. We know the next value in there is going to be 2, right? So I'm going to come in at 2. Oh, but what was the amount that I got for that inductor? If I go back to the inductor in here, something along those lines, that inductor had 20% probability, so I know I'm going to jump up 20% in probability. I'm now at half, right? So I'm at 0.5, something like that. The jump size itself, right, this little interval here, is the probability of an inductor, right? That's the probability that x equals 2. That would be the PMF value. And that's going to be held until what? Until I hit this value 2, which was the next thing. A value 2 is going to be my inductor, or not my inductor, my transistor. And a transistor occurs with probability 0.4. So I'm going to jump up now a value of 0.4. I'm going to go ahead and draw that in as well. So I'm going to get this 0.4. That's going to give me a total of 0.9. And that's going to hold for a while. And how long does it hold? Well, it holds until, right, I hit that last value, which was R, and that is a 5. So we had C, L, T, and R. We could put those guys in there, right? And this guy is going to be held until we hit that guy. And then there was only a 10%. We kind of knew that it was the last value. And once we get that, we've accumulated all the probability, and it better hang out at 1. Something like that. So we get a monotonically non-decreasing function that starts at 0, ends at 1. It has jump discontinuities that indicate the probability of particular events that are possible within our experiment. There are only 4 events that are possible in this experiment, so we're going to get 4 jump discontinuities. And the jump size of each one of those individual probabilities for those different events, in this case, a capacitor, inductor, transistor, or resistor. I'll finish out now my description. So I know that my CDF is going to be 0.5, starting at 0 and going up through, but not including 2, the next value, right? And it's going to be 0.9 for 2 less than or equal to x less than, so going all the way up until a resistor, but not including the resistor, so that's a value 5. And then we're going to be 1.0 for x greater than equal to 5, and I'm done. So very, very typical, I think, for a CDF of a discrete random variable to be piecewise constructed functions that just have these jumps, right? They have these jumps every time we hit an event that has some possibility, some probability. So let's go ahead and use this CDF now to find a few probabilities that we could have also gotten just from our initial statement, but I'd like to demonstrate how we can use the CDF to carry out these probabilities. So let's go ahead and first find the probability of a resistor, right? That's this guy sitting over here. I want to find the probability of a resistor. That is probability what? That's probability that x equals 5. And I know I can get that from the CDF by saying fx of 5 minus fx of just a little to the left of 5. If I compute those guys out, if I look at fx of 5, that's a value of 1, and if I look a little to the left of it, it's 0.9. So I would get, in this case, 1 minus 0.9, which equals 0.1. That should be the probability of a resistor. We go back up and we take a look at what the resistor probability was. It was 10%, so exactly like we expected it to. The next one, I think, shows a little bit of the utility, even though this is a pretty small or simple example. The next one shows a utility of using a CDF maybe over a probability mass function. In this particular case, I would like to know the probability that we had either an inductor, a capacitor, or a transistor, something on an interval, right? So I'm looking at what is the probability that I was an inductor, a capacitor, or a transistor, any one of those 3, right? How do I get that? Well, I'm going to get that from my fx of 2, right, minus, in this particular case, we want to include that guy, right? We want to include that guy going all the way out there. And I'm going to go minus x of minus 1.5, just a smidgen to the left, right? So we also include the minus 1.5 value, but nothing else, something along those lines. What does this whole thing tell me? This tells me that the probability that x, right, if I was looking at my x, was between 2 and 1.5 inclusive on both sides. The fact that I'm doing an inclusive part there is achieved with the CDF by using that little smidgen to the left, something along those lines. If you had a discrete random variable that had a whole bunch of values, like 1,000, and you wanted to know what the probability of that random variable being over a contiguous block of 500 of those values, you could get it as a simple difference of two CDF values. If you did it with a probability mass function, you'd have to add up the probabilities of all 500 values. So the CDFs can be really nice for finding probabilities of being over intervals. And it turned out our LCT here did give us an interval, right? We wanted to be on that interval minus 3.5 to 2 inclusive on both sides, something along those lines. So if I go ahead and I start computing this guy out, what do I get? Fx of 2 is 0.5, so I'm going to have 0.5 in there. And if I look just a smidgen to the left of what thing is c, so a little smidgen to the left of minus 3.5, I see that I get 0. So I'm going to get 0.5 minus 0, and that whole thing gives me 0.5. So I should have a 50% chance of being either an inductor, capacitor, or transistor. Let's go take a look at what we had for our original. So we are taking a look in this particular case. I want to know the chance that I was an inductor, a capacitor, or a transistor. That means I've got to add these four values up. 0.4 and 0.2 and wow, I've got something going on here. So where did I get this thing wrong? Probably because I misdid. So I'm glad I'm checking my work. We talked about that, right? Fx of 2, right? What is fx of 2? I missed it. It's 0.9. It is not that. This is a right continuous function. So at 2, this thing is 0.9. So let me go ahead and fix that. I can fix that pretty quickly on this one. So I'm going to get, in this particular case, a 0.9 minus 0 is 0.9. So I'm going to get 90% on there. Ooh, that looks a lot better. Go back to what we had as far as our check. 0.4 plus 0.3 is 0.7 plus 0.2 is 0.9. So 90% of the time we're going to have an inductor, right, a capacitor, or a transistor. And we could certainly get that off of the CDF. I think my mistake also helped, sort of accidentally helped illustrate this care that we have to take whether we include points or not. And a CDF, right, a CDF here does include whatever value you're including in there. And if I'm right on that boundary, well, then I've got to come up there. By the way, for those of you who have maybe not recently talked about things like right continuous versus left continuous functions, what is a right continuous function? Suppose I take a value 2. I'm going to go ahead and grab that. Let me do this in a different color. Let me go ahead and do it as blue. I'm going to go ahead and look at this value 2. I can look at the CDF of that value 2, and it looks like 0.9. What does right continuous mean? Right continuous means that if I step my way from the right-hand side towards that point, as those steps get closer and closer and closer, you're going to see the value looking closer and closer and closer to the value that I'm at. So we can see that fx of 2 is equal to 0.9. And as I step from the right-hand side over towards that point, right, I see that I'm at 0.9, 0.9, 0.9, 0.9. That looks like the value that I'm walking towards. That's right continuity. If I did the same thing, if I took the value 2 and I stepped from the left side towards it, right? If I'm stepping from that left side, I see I'm at 0.5 and it stays 0.5. It's going 0.5, 0.5, 0.5, 0.5, 0.5 until the very last possible way you could view it. You can't even really easily express it, that all of a sudden it just pops up to that next value. As I stepped from the left, I would get a total misunderstanding. I could get a misimpression of what the variables or what that function's value is, because this is not a left continuous function. Those functions, by the way, that are called continuous have both right and left continuity. That means if you step at a point from either the left or the right, they both go to the same value. You don't get tricked out on either side. In the upshot, this right continuous just means that if you get a jump discontinuity, you're going to get an open, right, so not including on the left, and you're going to get a solid or an including point on the right. And that has to do about these, whether we have things like less than or greater than and equals, whether it's a something or something and equals are all connected into this. And so we can certainly note that. The last one I'm going to do with the CDF, and remember, these are values for a pretty small example. They don't fully show some of the strength or the deficiencies of the CDF. It's just not a large enough number of outcomes possible in this discrete random variable to probably see that, but it does demonstrate how we can use it to find these probabilities. This next one, I want to find the probability of being an R or an L. Let's go ahead and do that with some green. Okay, so an R or an L. If I go back up here, here's my R, right, and here is my L. So I want to get both of those. Now we see that we're not on some interval, right? We don't have that interval going on there. We just have a value and we have a value. So I'm going to have to do this with differences of CDF for each piece individually, right? So I can do this as what was an R? That was x equaling 5. So this is going to be an fx of 5 minus fx of just going a little to the left of 5. And then I'm going to add to that what was my L in there? That's a value 0. So I'm going to have fx of 0, right, minus fx of 0 minus. By the way, this is the probability of a resistor. We saw that back up here, right? And this other one is a probability of an inductor. They're mutually exclusive, so we can just add their probabilities. If I go ahead and I do the calculations here, fx of 5, we see that is a value of 1. Fx of just a little to the left of 5 is 0.9. So I'm going to get 1 minus 0.9 and plus, and I go to the 0 in here. What is the value for 0? It's 0.5, and a little to the left of 0, it is 0.3. So in that particular case, I'm going to get 0.5 minus 0.3, so plus 0.5 minus 0.3. That's 0.1 plus 0.2 equals 0.3. So a resistor or a inductor should give us a total probability of 0.3. Let's go up here and check it out. A resistor or an inductor, that's those two lines there. And we can see in this particular case, we have a probability of 0.1 or 0.2, something like that. So add those two together, you get the 0.3 that we had seen on there. Great. So some simple examples of both constructing a CDF, sketching that CDF, using some of the properties we talked about CDFs to compute things like probabilities. I would also say that we can easily estimate a CDF using something called an empirical CDF. Let's go ahead and work our way through this as well. An empirical CDF is just something where we're going to estimate the CDF fx using observed data. For us to probably make good sense out of this, I do want to begin by defining what is called a right continuous unit step function. For those people who've had signals as a class, this will look very familiar. We talk about this unit step a lot. The unit step function, so u, it has some argument, has two values possible. It can be a 1 or a 0. If the argument is greater than or equal to 0, we're going to get that 1. If the argument is less than 0, I'm going to get a 0. So what does this thing look like? It is going to look like what we have sitting over here to the right. For anything less than that argument value of 0, right, I get 0. For that argument being 0 or greater, I end up getting that value of 1. So it's like a light switch. It turns something on. And notice that that is a right continuous function, right? So it's a right continuous definition of the unit step. And that's going to be appropriate for probabilities and doing things with the CDF because we know CDFs are right continuous functions. Okay, so what can we do with this? If we have a random variable and we observe some values, so I'm going to have some discrete random variable x, and I'm going to observe n occurrences of that random variable. So I'm going to get an observation x1, x2, x3, all the way out to xn. This is a little different than the xi's that we talked about before. The xi's before were those unique values found in the range space. These x's that I have, x1 through xn, are just the values that I observe in repeating this experiment n times. Some of those x's could be the same thing, right? If I had n, for example, as being 10, and my experiment was flipping a coin, right? It's very likely I can't get 10 unique values because it's either going to be a tail, value of 0, or a head, a value of 1. So if I flip that coin 10 times, I might find out that I get 4 tails and 6 heads in total. So I would see 4 of those x's all being 0, and I'd see 6 of those x's all being 1, something along those lines. So how can I use those observed values to estimate things like this CDF? I'm going to estimate the CDF, and I'm going to see that it's an estimate by putting a little hat over it. So my CDF estimate, so f sub x hat as a function of x, those are the observed values, right? It's going to be 1 over n, so 1 over the total number of trials, and then I'm just going to sum up a bunch of shifted unit step functions, and they're shifted by the value of my observation, right? So this shifted unit step, if I looked at something like a u of x minus xi, It's going to be a unit step, right? It's going to be 0 or 1, and this occurs when the argument x minus xi equals 0 or x equals xi. So I would get at xi for my value x, this whole thing is my u of x minus xi. It's just a shifted unit step. So what would this tell me? If I observe some value, xi, right, I'm going to throw in a little bit of probability to my CDF, but I'm going to weight it by the number of observations. If you do this all over for all n things, right, you're going to get a sum of n unit steps, each of height 1 over n. And if you add all of those 1 over n's n times over, you would end up eventually getting to an total accumulated probability of 1. So way off to the right, that's one of our properties of the CDF, the rightmost point is going to have to be 1 by this constraint. And way off to the left, before we could observe any values, the unit steps are all 0 there. So if I take n values at 0, it's going to be 0. And it's always going to be non-decreasing function, because these little unit steps always increase going to the right. They themselves are non-decreasing functions. So if I add up a bunch of non-decreasing functions, I get a non-decreasing function. I could also do this a slightly alternative way, but it's actually completely equivalent. We'll do an example on here. Let's let x, n sub x, be the number of our observations that are less than or equal to a particular value, and n just be the total number of observed values. So that's the number of times I replicated the experiment. My estimated CF is just that nx, that's a function of x divided by n. These guys here, right, these two things are actually equivalent. Let me go ahead and show this through a simple example, and then we should be pretty close to being done for today on this one. Suppose I roll a four-sided die n equals 10 times, and I observe whatever I observe from rolling that die. So here I go. I take that four-sided die out, and I roll it the first time, and I get a 3. I roll it again, and I get a 1. I roll it again, and I get a 4. I roll it again, and I get another 4. I roll it again, and I get a 3. I roll it again, and a 4, and then a 3, and then a 2, and then a 3, and then a 1. So I get 10 observations here. Because I'm only using 10 observations, I'm not going to get a perfect estimate of this CDF, but I am going to get an estimate. And as n goes off to infinity, that estimate is going to get better and better and better, right? So in the notation that we've used, my first roll is just going to be x1. That's the outcome of my first roll. x2 is the outcome of my second roll. x3 is the next roll. x4 is the next roll. And we notice that some of those x's are equal to one another, right? So which ones gave me a 1? Well, x2 and x10 both gave me a 1, right? What is n1? n1, if you look back here when we said n sub x, it's the number of those observations less than or equal to x, something along those lines. So if I look at n1, what are the number of observations that are less than or equal to 1? If I go through that entire list there, right, there's 2 values that are less than or equal to 1, so I get a 2 in that. If I look at the 2, I only happened in this particular time I rolled my dice 10 times, I only got one time that I got a 2 in there. So if I go and I compute that n2, recall that n2 is the number, right, of observations that are less than or equal. So it's an accumulation, if you will. So how many times did I see dice rolls less than or equal to 2? Well, I had a 1 that's less than or equal to 2. I had a 2 that's less than or equal to 2. And I had a 1 that's less than or equal to 2. That's a total of 3. I can get that by taking n1, right, that's that 2, and then adding in the number of times I occurred or observed that next value, a 2 in this case. So I get a 1 plus 2, and that gives me 3. The next one, 3, for this particular occurrence, when I did this particular experiment, I got 3s 4 times over. For whatever reason, I was lucky in 3s on this particular one. So that was x1, x5, x7, and x9, all giving me a value 3. What is n3? The number of occurrences out of my n trials, n is 10 in this case, that were 3 or less. Well, I had 3 from before that were 2 or less, right? 3 is the next value, and I had 4 of them, so that's a total of 7. And when I get to the last one, the 4s, I had 3 4s come out. That was x3, x4, and x6. And so n4, that being the last value that was observable, I'm going to get this whole thing being equal to n, right? The total number of observations. That's got to happen. If you have n observations, you're eventually going to plateau out with these n's, eventually getting to that overall n. So what is my fx hat? We could do it with the first method that we talked about, right, which was summing up a bunch of shifted unit steps, right, each weighted by 1 over n. My n is 10 here, so I'm going to sum a bunch of unit steps that are each 1 over 10. 2 of those unit steps are going to be shifted by 1. So I'm going to get 2 unit steps shifted by 1. I'm going to get 1 unit step shifted by 2. I'm going to get 4 unit steps shifted by 3. And I'm going to get 3 unit steps shifted by 4. And so I just combine them together in this way. That is one way of getting this estimated or empirical CDF. I could also do this based on those n values that we had before. So if we went ahead and looked at that, we know that at least for x less than 1, right, we had n being 0, so we're going to get nothing on that. Between 1 and 2, I'm going to get a total accumulation of 2/10. That came from this 2 sitting over here, n1, divided by the total number 10, so 2/10. Going from 2 to 3, once I hit 2, right, then I'm going to get that n2 value, right, all the way up until the next value occurred, which was at 3. That was 3, so 3/10 was the accumulation. And 3 to 4, I'm going to get the accumulation of 7/10. That came from this 7, the n3 value. And then I get 10/10 after I pass the final value, x equaling 4. In either case, if you plot them out, we end up with this empirical CDF in this case, looking like something that we should recognize, and that seems pretty clear. It starts out, whoops, that's not a good pen to be using for this, so let's get this back over here. It starts out at a value of 0, right? We know that CDFs need to start out at a value of 0, and then they accumulate probability, and because probability is always non-negative, right, it can only get bigger as we move to the right. When I get far off to the right, it has to go to a value of 1. So we start at 0 and end at 1, and we can never get smaller. At values that can occur, right, in this case we had 1, 2, 3, and 4. And it happens, we had a large enough sample size here, and we were lucky enough to hit all 4 values. It is possible that our empirical CDF would skip a value that was possible. If we chose an n that was small, right, and it's just through the chances of luck, never occurred in those n trials, you might not know that there was something there. So really for these empirical CDFs to work out pretty good, you do need to include a fairly large number of observations, right, something along those lines. And then what do we get here? So at 1, 2, 3, and 4, we get some occurrences. And from this, what would it seem? It would seem something like this. It would look like the probability that x equals 1 is 0.2. It would look like the probability that x equals 2 is equal to whatever the jump discontinuity size is there. That's only 10% there, or 10% of the number of observations, which we saw before. That's going to be 0.1. Probability that x equals 3, right, is going to be equal to, in this case, 0.7 minus 0.3 is 0.4, and probability of x being equal to 4 is going to be that 30%, 0.3. These are all estimates too, right? We're estimating these based on observations, and we know that there's some variability in estimates as we go. As n goes off to infinity, the estimates, right, will absolutely improve. Something along those lines. Now, before you totally discount this as complete garbage, right, you could sit there and look at that and say, hey, I've rolled a lot of four-sided die, and if it's a four-sided die and a fair four-sided die, like the kind you can just get in a typical gaming store, for example, they should each be equally likely. You should get 25% on each one of them. That kind of empirical estimate of the probability would not have been possible with a sample of n equaling 10. It's going to have to go by steps of 1/10 in this case. So we can already see through our choice of n in this case that it would have never been possible to actually get with little n equaling to 10, something that even by luck was hitting the actual value had it been a fair die. The other thing we don't know, and one of the reasons we use empirical CDFs, or we use empirical methods for finding probabilities, is we don't know, maybe a priori, or we don't have any guarantee that the die was fair. Suppose you were at some casino and you kept just getting crappy luck. You kept missing what you were sure was supposed to be a good thing. Well, you might sit there and suspect that the die were loaded, that they weren't really playing fair, and if you wanted to test that theory, you could throw those dice a whole bunch of time and get an empirical kind of calculation as to what their probabilities are. It certainly is possible a die could be loaded so that a 3 came up a lot more often than a 2, right? And we can figure that out through a large number of observations empirically by observing those random variables over and over and over again. That's enough for now. Next time, we're going to move into probably the strongest reason why we ended up choosing to look at random variables where we assign outcomes to numbers. And that's so we can start doing the math of averages. So we're going to talk about things like modes, medians, and expected values. Super important topics. That'll be next time.